Hello, I'm Brennan, and these are my group members, Jimmy, Theo, and Marcel, and we're from 4J. In this video, we'll be explaining on concepts of electromagnetic induction behind the operation of a transformer. We will also be sharing the process of the construction of a model and explain why we decided to construct it in this way.
Firstly, it is important to understand Faraday's law, which is that EMF is induced whenever there is a change in magnetic flux linkage. Magnetic flux refers to the amount of magnetic field passing through a surface. It can be calculated by the product of magnetic field strength and the surface area. In other words, if the magnetic field strength at two areas are the same, but the area is higher in one area than the other, then the magnetic flux at the larger area is higher. What exactly is a transformer? A transformer is an electrical device that transfers energy between two or more circuits through electromagnetic induction. Varying magnetic flux linkage induce EMF in the secondary coil. A transformer can either be step up or step down. If the voltage in the secondary coil is more than the voltage in the primary coil, it is a step up transformer. However, if the voltage in the secondary coil is less than the voltage in primary coil, it is a step down transformer.
Moving on to the construction of our model, let's first take a look at the materials which we have purchased. 30 meters of copper wire, a multimeter, 4 DC batteries, batteries holder, a ring-shaped soft iron core, crocodile clips, and a switch. This is a simple drawing of the transformer model that we will be building. As you can see here, the soft iron core is coiled at two separate areas, and this forms the primary and secondary circuit. Another thing to note is the difference in the number of coils in the primary and secondary circuits. We will have more coils in the primary circuit than in the secondary circuit, which makes our transformer a step-down transformer. Without further ado, let's now start building a transformer.
We have chosen copper wire as it has a very high electrical conductivity and is a relatively common metal. We have already coiled the copper wire around the soft iron core beforehand. For this model, we will have 50 coils on the primary circuit and 20 coils on the secondary circuit. Additionally, we also sandpapered the ends of the copper wire because this helps to remove enamel from the wires, improving electrical connection. Soft iron can be easily magnetized and demagnetized and has a unique ability of concentrating magnetic fields. This is important in a transformer as the magnetism of the core has to be changed easily to induce voltages in the secondary circuit. Additionally, we have chosen to use a ring-shaped soft iron core rather than a soft iron rod because a ring-shaped soft iron core is able to prevent magnetic field lines from being dissipated outside the iron core and is able to confine magnetic flux within the soft iron core so as to make the transformer more effective and efficient. Now that we have completed the coiling of the wire around the iron core and the sandpapering on the wire ends, we can now complete the circuit by adding the batteries and other electrical components to the circuit. We first connect the batteries to the switch and the primary coil with the help of crocodile clips, before connecting the multimeter to the secondary coil. The multimeter here serves to detect any voltage in the circuit to see if our transformer actually works. We are finally done with the construction of our transformer, and this is our final product. Let's test if it works. As you can see, when the switch is open, the reading on the multimeter is 0. As we now close the switch, we see a momentary change in the reading, but the reading returns to 0 shortly after. The reading when we close the switch is positive. As we now open the switch again, we see that there is a momentary change in the reading again, as we record a negative reading. As we try this a few more times, we see how this observation remains true. Now, we will be going into the details of the application of our model and how it actually works. This would also explain the momentary changes in the multimeter readings whenever we open and close the switch, which cause us to obtain negative and positive readings respectively.
When current goes through the primary circuit, a magnetic field is set up in the coil. The magnetic field is linked from the primary circuit to the secondary circuit via the soft iron core. This causes flux linkage in the secondary circuit to increase momentarily. Momentary EMF is induced according to Faraday's law, hence causing the momentary change in multimeter reading. However, when the current being received from the primary circuit is constant, the flux linkage remains constant. Hence, no EMF is being induced, which explains the reading of 0 after a while. When the switch is being reopened after that, flux linkage in the secondary circuit decreases. A current is being induced in the secondary circuit, but this is momentary as well. This causes a momentary change in multimeter reading once again. However, this time a negative reading is recorded because the flux linkage is decreasing. As we have mentioned before, we have 50 coils on our primary circuit and 20 coils on our secondary circuit. This is a turn ratio of 5:2. The turn ratio, or the number of coils, should be equals to voltage ratio. This means that the voltage recorded should be proportional to the number of turns of coils. Hence, mathematically speaking, since we have 50 coils and 6 volts on the primary circuit, we are expected to have 2.4 volts on the secondary coil when we have 20 turns. However, in this aspect, our model is unable to perfectly step down the voltage according to our turn ratio. This could be due to the fact that our circuit components are not ideal. More importantly, this can be attributed to the fact that we used a DC supply instead of an AC supply. In a DC supply, since there is no change in direction of a current, a steady magnetic field is set up, and voltage will not be induced in the secondary coil except when we open and close the switch. In AC, since the voltage is varying in magnitude and direction, a rapidly changing magnetic field is set up. This changing magnetic field is linked to the secondary coil via the soft iron core and induces an EMF in the secondary coil.
This J Fox. Met this girl at the club, man. Check out how it went down. I see a pretty lady sipping on a drink. I gaze into her eyes, then our glasses go clink. And I know I want to chant all over her Tatum.